grouping. So we're starting with a general counting principle for when we have groups, when we're grouping. So first of all, we mentioned this last lesson. First of all, you want to order the groups that you have, because some of them, if there's people that want to be in pairs, they make a group of their own. So first of all, work out how many groups that you have and put them in order. And then you need to order the individuals within each group. Okay? A group can sometimes just be one person, or it could be multiple people. So, examples. In how many ways can 5 boys and 4 girls be arranged on a bench if there are no restrictions? This is not new. I have 9 people there. It doesn't matter if the boys and girls part at this stage.
5 people.
No, easier than that.
9 squared. No, 9
factorial.
9 factorial. Yeah. Okay, all I'm doing is I'm putting 9 people in order. So 9 factorial. That is the same as 9p9. If you prefer that notation. So that is 3, 6, 2, 8, 8, 0. Okay, now the reason I mentioned the boys and the girls is because of the other questions that are coming up now. So part B says the boys and the girls are going to alternate. Now, it could be, well, actually it has to be, there's 5 boys and there's 4 girls. There's more boys than girls. So what am I going to have to start with to make them alternate?
Yeah.
Boys. Okay, the boys are going to have to be at the end so that the girls can be in between. So in my little box here, I'm going to go boy, girl, boy, girl, boy, girl, boy, girl, boy. Okay, so that's my 1, 2, 3, 4, 5 boys, and my 4 girls are in between them. Okay, that's the only option for that because I had more boys than girls. Sometimes it could actually work both ways. I could have boys, girls first, or girls first, but we'll get to that. All right, so we have to order each one of those groups. Let's think of them separately. So first of all, the boys. I have 5 boys. How am I going to order those boys? 5 factorial. 5 factorial ways of ordering the boys. And then I have the 4 girls to order in between them, and that's going to be a 4 factorial. So we just times those together. You could have also written that as 5p5 times 4p4, but factorial notation is shorter if you're putting all of them in order, right? That equals 2880, so much less now that we've got some restrictions in there. Okay, part C, the boys and the girls are in separate groups. So it's either we've got all the boys sitting together on one end of the bench and all the girls sitting on the other end of the bench together. But which way would they go? So we've got a few things to consider here. We've got 2 groups. First of all, we want to order the 2 groups. How many ways can I decide? Is it going to be boys first? 2. There's 2 ways I can arrange those 2 groups. It is 2 factorial. If there was 3 groups, I would have to go 3 factorial. But 2 factorial is equal to 2, so that's just shorter, right? Then I want to order the boys. How am I going to order those boys? 5 factorial. Same as before. And order the girls, which is 4 factorial. So you're timesing those things together and you get your answer, which is 5760. Anne and Jim, so Anne we assume is a girl and Jim we assume is a boy, wish to stay together. So how are we now going to order the people on our bench? So if 2 people have to stay together, we consider them a group.
5p4 times 4p.
We don't actually care about the boys and the girls being separate anymore. All the rest of the group can do whatever they want, no restrictions. It's just those 2 people that need to be together.
8 factorial.
I think 8 factorial, yes? Yes. So there's now 8 groups because 2 of them have become one group. But because it could be Anne and Jim or Jim and Anne sitting on that bench, we have to order that couple by timesing by 2 factorial or 2. Okay, timesing those together. And we get 80,640. All right. We touched on this next part last lesson. We did a little preview on it, but we want to talk about it some more. In the previous exercise, we learned about NPR. which is the number of possible arrangements for an ordered selection of R objects from a total of n. So if n is my total number and I want to order R of them. So if I have 9 people and I want to order 3 of them, I'd go 9p3, okay? But when the order is not important, so AB is the same as BA, the order that their people are sitting in is not important, then the number of arrangements is called a combination. And that's why I gave you that worksheet to start identifying when is the order important and when is the order not important. There were some tricky ones on that worksheet. Okay, now like the permutation, the combination has a formula. Do you remember the one for a permutation?
Was it an n factorial of n minus r?
Yes, it's that part there, n factorial over n minus r factorial. The only difference for the combination is that you want to divide by an r factorial, which is the number of people that you're putting in order. And that is dividing away the number of different, if you selected 3 people, it's dividing away the 3 factorial different ways of arranging those 3 people. You're dividing out the repetition part. Okay, so if I chose ABC, I don't want CBA and ACB. I'm dividing out the different arrangements. Does that make sense? Kind of what that's doing?
Yeah.
So the formulas are very similar. The proof. Do we want to go through the proof? Do we like the proof?
Yeah.
No.
No. All right. Maybe let's leave it because I'm not going to ask you to do the proof and we get more time for questions if we keep going. All right. Example number 2. If 12 coins are tossed, find the number of ways of tossing 7 tails. Do I have to get 7 tails straight away? Is the order, do I have to get 7 tails and then 5 heads? No, I just need 7. Doesn't matter the order that they come in. So the order is not important. It's a combination. I'm going to toss the coins 12 times and I just need to get 7 tails. So 12C7. Order is not important. Okay, so there is 792 ways to get 7 tails. Okay, committees are another time when it's usually a combination question. A committee of 5 people is formed randomly from a group of 15 students. In how many ways can the committee be formed? It doesn't matter who is picked first or second or third or fourth for the committee, as long as you're in the committee. So it's 15 people and I just need to choose 5.
3,003.
It seems simple now, but that's because you know these ones are going to be combinations. You're going to have to, on your test, you're going to have to read, is this a combinations question? Is this a permutations question? You're going to have to work out which one's which. Question 4. If the above committee is chosen from 9 seniors and 6 junior students, in how many ways can I pick 3 seniors and 2 junior members for the committee of 5? So I'm just splitting that up into 2 groups. So from the 9 seniors, I need to pick 3. So that's going to be 9C3. Then from the 6 juniors, I need to pick 2 of them. So 6C2. Times together, there's 1,260 ways to form that committee. Making sense so far?
Yeah.
Wonderful. Question 5. In how many ways can a committee, so you hear that word over and over again, they love their committee questions. In how many ways can a committee of 3 men and 4 women be selected from a group of 8 men and 10 women? That's very similar to the last question. I have 8 men in total and I need 3. So it's 8, oh, that was a messy 8. 8C3 times by, now I need the women, I have 10C4. If you did it the other way around, it's the same. You could do the women first. It's multiplying, doesn't matter which one goes first.
I have a question about number 4. The one.
Yeah? Do you want to ask me now or later?
Yeah, now.
Yep.
It says the committee of 5. How do you know about?
Oh, because it was still saying from that last question where we had a committee of 5 people. So it did say that I wanted 3 seniors and 2 juniors to get my committee of 5. It's just telling me the total at the end.
Okay.
Yeah. Okay, next page.
Last page.
A general counting principle, like usual, deal with the complementary situation. This is a little bit different. So sometimes it's actually tricky to think of all the different possibilities that you can arrange something. Sometimes it's easier to think of the complementary situation and to subtract it from the total. Okay, so remember like in probability when we did, let me think of, rolling a dice. That's a very simple example. We could say rolling a 6, we have a 1 on 6 chance, but the complement of that would be the 5 over 6 chance. Sometimes it's easy to work out what it can't be to help you work out what it can be, is what that's saying. All right? So example 6. In how many ways can words be made from the letters A, B, C, D, E, and F if the vowels must be separated by at least one consonant? Okay, so that's where the trick comes in. We don't know, there's 2 vowels there, right? We don't know if they're separated by 1 consonant, 2 consonants, 3 consonants, and there's a lot of different options that we could do there. So instead, if we put those 2 vowels together and made them together, we would want everything else. We would subtract that off the total and everything else would be what I want. Yeah, so that's what we're going to do. Mm-hmm. So first of all, we need the total. So no restrictions. Pretending there's no restrictions, we need the total. That's right, there is 6 letters there. So 6 factorial ways to arrange those letters. There is 720 ways if there was no restrictions whatsoever. Now, we want to put those 2 vowels together. Almost, yes. 5 factorial is the start. Okay, I'm putting the 2 vowels together, which makes 5 groups, but yes, Isaac, I still have to multiply by 2. Okay, because there's 5 groups, but I still have to order within that group. The A and the E is different to an E than an A. So times by 2 factorial or 2. So there is 540 ways to put the vowels together. So that means everything else has the vowels separated, right? So the vowels apart is that total 720, subtract off the ones where they're together, which means there's 480 ways of arranging those where the vowels are separated. Yes, it's the complementary event. Next one, and this can be a bit of work sometimes this one. A general counting principle using cases. Sometimes we can't use the complement. Sometimes we just have to work out all the different options and add them together. So you have to make sure, first of all, that your cases don't overlap. Okay, there can't be things that you're counting twice. And if they do have an overlap, you're going to have to subtract off that overlap, aren't you? So example 7. How many whole numbers less than 2,000 are odd and greater than 1,000, or multiples of 10 and less than 800?
Hi.
Hello.
Can I say Jessica? Please.
No worries. So we do have a few different situations here. So first of all, we have odd numbers between 1,000 and 2,000. That was my first thing. How many whole numbers less than 2,000 are odd and greater than 1,000? I've just reworded that, okay? So between 1,000 and 2,000, how many odd numbers are there?
500.
500, yep. So there's 1,000 numbers and half of them would be odd. So there would be 500 odd numbers between 1,000 and 2,000. The second part of that question said multiples of 10 less than 800. Okay, so let's do that part now. Multiples of 10 less than 800. So just thinking of that scenario, 80, correct. Is there an overlap? So the first one I was looking between 1,000 and 2,000, and the next one was less than 800. There's no overlap, okay? So there's no overlap there. I don't have to worry about, I'm going to write a note there, no overlap. So we remember that, no overlap. So all I have to do is add those two amounts together. 500 plus 80 makes 580. Not always going to be that simple. Let's try B. How many whole numbers less than 2,000 are multiples of 10 greater than 500 or even numbers less than 1,000?
That's too many words.
One bit at a time. Okay, so the first part, multiples of 10 between 500 and 2,000. So multiples of 10 between...
How do you get that out of that word?
So how many whole numbers that are, so it says here, how many whole numbers that are less than 2,000, they've got to be multiples of 10, but they're greater than 500. It's just worded in a, they could have just said exactly what I've written there, but they've worded it in a complicated way. So it's that first sentence.
Okay.
So, thank you, Isaac. Yes, 150.
How do you figure that out?
Because there's 1,500 numbers between 500 and 2,000, and multiples of 10, you just divide that by 10, right? So 150.
Yep.
The second part of the question was even numbers less than 1,000. How many of those are there?
This is all though.
Yep,
500.
we'll get to that part.
500.
Yes, there are 500. Good.
600.
Even numbers less than 1,000. Okay, and so if there's 1,000, you count into 1,000, then half of those numbers are going to be even, right? 500. Is there an overlap?
Yes.
Yes, there is. There is an overlap of even numbers that are multiples of 10 between 500 and 1,000, isn't there?
Yeah.
That's our overlapping section. And there's 50 numbers. Good job. Well done. All right. I'm writing it all down in words so you can follow it later if you need to read through it again. So the overlap is the even numbers that are multiples of 10 between 500 and 1,000, which is the 50. There's 50 numbers. So because there's 500 numbers between 500 and 1,000, and multiples of 10, divide that by 10, there'd be 50 numbers there. So basically what that is doing is I had 150 for the first thing, there was 500 for the second possibility, and I subtract off the overlap, which gives me the answer. Now, instead of all those words, this could ring some bells with some notation that we used last year. If A was multiples between 10 and multiples of 10 between 500 and 2,000, we could go the number of elements of A is 150. The number of elements of option B was the 500. The number of things in A and B, that's your overlapping section, was your 50. You remember that notation?
Yeah.
And do you remember this lovely formula? If I want the number of things in A or B, anyone remember it? Nope.
A plus B.
Number of things in A plus number of things in B minus the overlap. We learned that formula last year. Admittedly, the questions weren't quite like this, but we did use that formula last year. Okay? So you can also use that kind of notation. You get the same result, as long as you are confident that you clearly know what A and B are going to be. Yeah, we did use a Venn diagram to show where the overlap was. You got A is that set, B is that set. We want to subtract off the overlap so we know the possibilities of A and B.
Do we have to do that?
Yeah. No, either option is fine. I don't mind which one you use. And that's it. That wasn't so bad.